All right, getting into volume using integration. So here are your basic concepts. The volume equation is pi from the lower bound to the upper bound of some radius function squared dx. Pi r squared coming from the area of a circle, because basically we're going to have a bunch of circles stacked on top of each other, and we use integration to find volume. So let's look at the first figure. I guess a couple things to notice if we can. If we're talking rotation around the x-axis, which is the line y equals 0, or perhaps another y equals line, a horizontal line, then the radius function will be perpendicular to that axis. All right. So in this particular case, when we rotate around the x-axis, then r of x is the distance from the x-axis up to the function, which in this case is the y value, which is rad x. So the little radius function here is rad x. A and B are both going to be x values whenever we rotate around something horizontally. All right, these are f of x functions. F of x is equal to rad x, so the x value. So let's take a look. This is an x value of 0. This is an x value of 1. So our two bounds are 0 and 1. The function f of x is equal to rad x, so we say rad x squared. This is pi r squared. And then we just set up and solve the definite integral, and I'll leave that up to you, but that's your basic concept. Again, whatever you're rotating around the axis, we draw a perpendicular line up to the function and we determine what is the length of that segment. In this particular case, it'd be the y value, which is rad x. Okay, let's go to something a little different. Let's take the same graph, but let's rotate this around the line y equals 3. So this is what we call washer method. So instead of a solid circle, it'll be a circle with a hole punched in the middle of it. So it's going to have two radius functions. So again, what we're going to do is we're going to circle our axis of rotation, which is the line y equals 3. Our bounds are still x bounds. They're from 0 to 1. The pi r squared is still going to be the same, but in this case, we're going to have a big radius function squared minus a small radius function squared. So the big radius, we're going to start here, and we're going to work our way down to the first function, which is y equals 0. So this is length is going to be 3 all the way down to here. So our big radius function is just the constant 3. Okay, the little radius function, since the distance between here and here is rad x, the distance between here and here is 3 minus rad x. So again, if you're coming from the other direction, we know that the distance between the axis and this point right here is rad x, so 3 minus rad x gives you the small radius function. So again, like we talked about before, big radius function squared, 3 squared, minus little radius function squared, 3 minus rad x squared. We went ahead and foiled that out, combined some like terms, rewrote it one time with a fractional exponent, and then we just did our inverse power rule, our f of b minus f of a, and we come up with 7 pi over 2 for an answer. One more little possibility here. So this time we're going to rotate the thing around the y-axis. So here's two switches. Number one, equations should be solved for x. They're going to be like f of y equals this, or g of y equals this. The second thing is the bounds should be y values also. Other than that, the other part is still the same. So if we start on the x-axis, the big radius function going all the way out to the farthest point, this thing is actually bound by the line x equals 4. I changed this one up a little bit. I used x equals 4 because I wanted to make sure you saw the difference between y bounds and x bounds. Okay, so let's look at the bounds. So this thing is bound from here to here, y values. This is y is equal to 0, and the y value up here is only 2. All right, so from 0 to 2 of the big radius function squared, we're going to go all the way out here to the line x equals 4 minus the little radius function squared. So if I have y equals rad x, then also if I square both sides, x equals y squared. So the little radius function was y squared. So again, I've got big radius function squared minus little radius function squared. These are both solved for x. And then these values here are y values for the bounds. So I go ahead and work this out. I'm integrating with respect to y this time. I knock it out. I use the antiderivative power rule. I wind up with 128 pi over 5. That's good for the day. Homework follows. And we'll do a couple of calculator problems at the end where you just have to set it up and solve it in the calculator. Thanks.